So previously we've used the ADC, or analog to digital converter, in order to input an analog voltage and convert it into a digital signal that can be input into the microcontroller. So some microcontrollers also contain a DAC, or digital to analog converter. So this is able to output an analog voltage. So these DACs are very useful for audio type applications, because we can, rather than outputting just a voltage of 0 or 3.3 for example on a GPIO pin, we can actually output any voltage in that range. So we know for an analog signal, for example, we could have a digital representation of a signal, then output it, convert it back into analog signal using a DAC. So you got some original analog signal, goes into an A to D, is converted into this digital representation, which is then transmitted. So this will be the kind of receiver, if you will. Sorry, transmitter and receivers have a DAC on it. So get that digital signal and convert it back to an audio signal. What can they output through a speaker or whatever? So digital outputs, we can either output a discrete 0 or 1, just 0 volts or 3.3 volts, nothing in between. But with a DAC, we can output an analog voltage. So for the NXP LPC 1768, we can output a voltage in the range 0 volts to 3.3 volts. So the DAC in the microcontroller is a 10-bit DAC, meaning that there's 2 to the power 10 or 1024 different levels. So the resolution, to get the kind of difference between each of those steps, we've got the maximum voltage is 3.3 volts, which will correspond. So these digital levels essentially go from 0 to 1023. So 0 will obviously correspond to 0 volts, and 3.3 volts will correspond to 1023. So the the difference between each step, or the resolution, is 3.2 millivolts. So the DAC in the LPC 1768 uses what we call a resistor string architecture. So this is actually very, very simple. So an n-bit DAC requires 2 to the n resistors. So that is a lot of resistors. So inside that microcontroller, we've got this 10-bit DAC. So we've got 2 to the 10, 1024 resistors. And these are all chained together. So essentially they form a very large potential divider. So you can see here we've got this resistor string, 3.3 volts at the top, 0 at the bottom. So each node, has essentially got a different voltage. You only had 2 resistors, you'd have like, have the same resolution. And all these resistors, I should put, are the same, typically the same value as well. So all of these nodes have got a different voltage, different analog voltage associated with them. And then these will go into kind of like a multiplexer. So then this will be the kind of control bus. So by specifying which node to output onto output will control what the output voltage is. So for example, I think there's 8 here. So this, if we say this is 0, so that's 111. It'll start from here, 0, 0, 0, 0, 0, 1, 0, 1, 0. So depending what value we put here onto this select bus, we can choose which voltage essentially to feed through into the output. So it means we can get, rather than getting 0 and 3.3 volts, we can just pipe whichever voltage we need to the output. So this is how we get the analog voltage on the output. So we'll look at this microcontroller block diagram. You can see the DAC is just another peripheral. So this again, it's separate from the, we've got the CPU, the core, different memory, so it's connected via this bus system. So it means in our software what runs, we're able to interact with this DAC. So on the embed, there's actually only one DAC output. That's on pin 18. So you need to make sure that you use the correct pin when using that. And this is where the DAC lives. So the DAC is in this APB1 peripherals within this memory address. So all the registers inside the DAC peripheral live within these memory addresses.